You have this neurovascular bundle that travels in the bone canals, right? And you have cells, all these cells. And so we've been here repeatedly, and you should look through the video library that Dr. Carl has on the works that we've done here before, and you can get refreshers on the bone anatomy and the kind of tissues we're finding. But we're finding the stuff that other people aren't finding. We're following the paleontologists to their digs, and we're digging right where they dug, and we're finding things that they're not finding. How's that possible? But it's happening, and we're publishing it. So soft tissue is a big component of it. And you're going to see some of that today. Maybe not so many cells, but you can go onto our website. We have videos. You can watch videos that we shoot through the microscope and see these preparations yourself. But just to familiarize ourselves with what we're really talking about when we talk about dinosaur remains or even Permian remains, I brought K-Cops with me today. This is supposedly one of the oldest tetrapods, terrestrial tetrapods on the planet, and that's actual size. And we have nerves from this guy today, which is about to be published. And that's much older. The dinosaurs are typically Cretaceous. It was a span of maybe 40 million years, between 68 and 100 or so. But Permian stuff, that's supposed at 250 million years in age. And so you're going to see this new work today. But that's the refresher. When we're talking about dinosaurs, we're talking about their bone and the elements that are in their bone. Now here we go with more clots, and I'm calling them clots. I am attesting or challenging the scientific community to see the clots in their own specimens. I'm not telling them to look at my specimens. I've already proved that there are clots in my specimens, to my satisfaction anyway. And we'll talk about that a little bit. Blood clots. Why are blood clots important? You heard about blood clots during COVID, didn't you? A lot of people who died from COVID, from the disease, had clotted blood. Have you thought about that? Have you thought about why? How? Clots are significant. And they're showing up in every single preparation we do. By the way, Carl, I want those Camarasaurus specimens back. Okay? I want them back. I need to look at them some more because I found some astounding things in there, and I've presented them here before, that need to be explored further, and that Camarasaurus may be the key for that. But we'll have to work on those together. So clots, we found clots in 7 different individuals, and I'll review that in a second. So we're finding them across taxa. We're finding them across deep time. Clots. Why? It's interesting. So here's another clot paper, and this was Nanotyrannus. Now we chose this organism, Nanotyrannus lancensis. Why? It's controversial. It's a kite that's already in the air. So all we got to do is tie another string to it. And so that's what we did. We went hunting for Nanotyrannus. There are 2 schools of thought on this organism. One is, it's just a pygmy dinosaur. Jack Horner, that's just a pygmy dinosaur. Sorry, T-Rex, yes. I'm thinking ahead of myself. It's just a pygmy T-Rex, thank you. My staff is much more brilliant than I am. That's why I appreciate them so much. Just a pygmy T-Rex, just a little T-Rex. But there are anatomical features in Nanotyrannus that are different from T-Rex. For one, they think it ran 60 miles an hour. Now, it didn't do that. The T-Rex didn't do that in Jurassic Park, certainly. But this guy supposedly could. He also has different teeth and different numbers of teeth. But the teeth is diagnostic. How do you know you got Nanotyrannus? We got the tooth and the claw. You'll see those as we go through this presentation. So we know we're dealing with this organism according to the paleontologists who are on site. So we collected in Montana several different bones at this site, which you're going to see, and we tested them for clots. Now, how do we do that? We have to thin section the bone. So we can't look at the whole bone. I mean, we can, and we've done experiments where we see clots coming all the way out to the surface of the bone. So we've seen that. Just on the outside of the bone, you can see the vessels that terminate at that surface, there's clot material right at the surface. And it goes all the way into the bone. How do we know that? Because we thin section them. And you can see these clots traversing the whole bone. And so here's a radius. This is a small limb element, very delicate. And we thin sectioned it, and here's a clot in that bone. You can see structure in here. You can see those black dots. Those are all the cells. Remember, we could go back to our original diagram. All these little dots in here are the cells. Here's one magnified. So these are cells. And this is a canal. That's a canal. It's an oval canal. They look round when you're young, but as you age, they change shape. Your entire skeleton is remodeled every 15 years based on what the cells do. They're busy fixing your bones all the time. So that's what you're seeing. You're seeing the cells surrounding the canal, and the canal is dark. I'm putting light through it in the microscope, but it's completely dark. Why? Well, I believe that's the clotted blood. And we invented, or didn't invent, but we took advantage of a special microscope called an ultraviolet microscope, and we're exciting the iron. So the iron in here is glowing. It's autofluorescing. Let me give you an example. Remember when Moses went up to speak to God on the mountain? He spent a long time up there. He came back down, and the Israelites did what? Moses, Moses. What did they tell him? Can't hear you, class. Put a veil on, right? Why? Because he was glowing. Cover your face. That's autofluorescence. Your skin, the proteins in your skin will glow if I irradiate you with the right UV wavelength. And so here's the iron saying, I'm here because it's autofluorescing based on the UV light. So this is the test. And this is now the 7th individual. So it's all in the literature. You can go on our website and download all the papers. So the radius, positive for clots. This was published last November. Here's a digit from the mantis. Call it a phalanx. Here is cells around the canal. Here's the canal, just like our little diagram. Right? Here's the canal. Looks the same in this picture. It's a nice round canal. See that? Here's all the cells around it. Autofluorescent. Why? Clotted blood in the center of the canal. Here's, according to the literature, what we have to call a postcranial element, probably a limb bone. A lot of this stuff is shattered. We dig it out of a sand wall, but it looks like it was tumbled in a cement mixer. Everything's fractured, broken apart, separated. Sometimes you find well-articulated specimens, but where we dig in Hell Creek, not so much. They call it reworked. But positive for clots. Haversian canal. Canal is filled with the iron. Now there's a theory of preservation. How is this tissue still here? You might have asked yourself, how can these cells be here? How can these blood vessels? And it's all in our previous presentations. Dr. Carl has it all online. You can see it all. How can this stuff still be? What's preserving it? Is it frozen? No, because in Montana you have freeze-thaw cycle every year. Freeze-thaw, freeze-thaw. So it's frozen and refrozen every year. There are radioactive minerals in the ground, so it's getting irradiated. There's all kinds of predators, microbes, bacteria, insects, protists, worms. And I'll give you a little preview. We found living worms in these bones. I thought they were dry, dusty rock. Why would they have worms in them? Well, I don't know. You can tell me. So clots. Now clots are important. Why? Because it shows us how they died. How they died. Here's a postcranial vertebral element from Nanotyrannus, probably a tail vertebrate. It's rounded. Why? It's been tumbled like in a cement mixer. And here's a thin section. Remember, we're cutting a thin section. It's about half the width of one of your hairs. Cutting through and taking only that to examine. Here's a beautiful clot. And the clot adheres closely to the canal wall. Look at how butted up against the wall it is. And it doesn't leave the canal. You see it leaving the canal? They say the iron from the blood went out and it preserved all the tissues all around it. Well, I don't see it leaving the canal, do you? My UV microscope shows it all in place there. So, clots. Here's the ulna, another limb element, positive for clots. Haversian canal, here's the canal jammed with a clot. In some pictures, in these pictures, the clot is moving directly away from us, so it's a nice cross-section. Sometimes the clot is going in an angle, and so you get an elongated image of that clot, so you can see it descending through the bone, through the whole bone. This shows a little bit of that. That's descending down, because these are 40 microns thin, yeah? And Dr. Carl's going to start making our slides for us here. Get that laboratory humming, right, brother? So clots, clots, clots. Here's the claw. We got a beautiful claw. I'll tell you a story, too, because you need to come on a dig. For two reasons. Number one, we're getting old and I can't do it anymore. And second, Keith is getting old and he can't do it anymore. He's our pack mule. So we try to give away bone shards. We gave away how many bone shards in Las Cruces? Every student gets a bone shard. So we need to collect like 100 bone shards every time we go on a dig. So come with us on a dig, and you'll sit in front of a wall of sand that they just take a grater and make this wall. And when we first started, I brought screwdrivers because I thought, well, what do you bring to a dig? I brought a screwdriver and a paintbrush. I threw them in a bag. I didn't want to show them to anybody, show my ignorance about how to dig dinosaur bones. And we got to the dig, and the guy said, go grab some tools. And I went over to the bag, and there's screwdrivers and paintbrushes. So I thought, I'm doing okay. But we're digging with our paintbrushes against this sand wall and picking away because I didn't want to hurt anything. And Clayton Phipps, I don't know if you've heard that name. We were digging with Clayton. He was on the Discovery Channel. They call him Dinosaur Cowboy. Great guy. He pulls out a Bowie knife that's about 9 inches long and slams it into that sand and pulls it out on his chest, and claws and teeth fell out on his chest. I thought, wow, I'm doing it the wrong way. But if you do come, be prepared to pay the dig operator for that. Because this is how they make it. A lot of them are homeschoolers, We want to support them. But claw, positive for clots. So you can say, this guy clotted to his claws, but not to his teeth. And here's the diagnostic Nanotyrannus tooth I mentioned. It's double serrated. It has a serrated edge here, serrated edge here. It's a little bit different. The T-Rex teeth are a little bit different than this guy. And this one has more teeth. So I'm of the opinion that it's a separate taxon. But a lot of people don't think so. Okay, back to the clots. So I'm saying these are clots. I'm saying this is the result of the animal's death. Because there is a known condition, several terms for it. Hypercoagulopathy is one. It has to do with coagulation, which is blood clotting. And recently, we read part of Michael Behe's book, Darwin's Black Box, on the blood clotting cascade. And I'm going to have Ruth come up and expound exponentially on how complex. No, she's not. But pretty complicated, wasn't it? We barely could understand all of the proteins and cofactors that come into clotting. It's a highly engineered system. But it is telltale if you drown. When you drown, your blood clots. If you stay dead from drowning, your blood is clotted for the duration until your decay is finished. And so, if you're rescued from a drowning event and brought into an ER, and they're trying to resuscitate you, if they get your heart pumping again and you're breathing again, oxygen going through your system, now you're bleeding out. You bleed out. Why do you bleed out? Because all the reactants that were used in that one-way coagulation cascade are used up. So it's going the other way now. I've said this how many times? Last time in Las Cruces, I stood there and said, ask any ER physician And there was an ER physician in the room. And I didn't know it till he came up to me later and said, "Good talk." So my contention is these are clots. These organisms drowned. And the telltale sign of how they drown is in the clots that perfuse their bones. And so we found them in all these different individuals. Triceratops, it was horn, frill, vertebra rib. Nanotyrannus, you just saw that. Camarasaurus, I don't know what bone that was, Carl, but it had the most beautiful protein autofluorescence that I've ever seen. So we want to investigate this more. This, I think, has good future. Dimetrodon, you guys know who Dimetrodon is, right? The sailback guy. I brought one of his teeth today, so if you need to pick your teeth, it's real hard. Just come up and let a Dimetrodon pick your teeth for you. K-Cops, you're going to learn about in a minute. We found clots in him, that little Permian guy. Eriops, he's about 10 times bigger, but same time period. And now an Edmontosaurus. Now, Jack Horner said to Mary Schweitzer, when she said, "I think those are red blood cells," prove to me they're not. To my knowledge, has she ever proven that they're not blood cells? I mean, we know they're framboids. The Camarasaurus, we shot the most beautiful cross-section of a framboid I've ever seen. The most beautiful UV autofluorescing, and the green protein inside of it, fluorescing also. And so, what if it's just an exploded red blood cell? You know, it's got iron, it's got oxygen, and it's got protein. That's what blood cells are made out of. So it wouldn't surprise me if that Camarasaurus is a perfect example of that. But how do you prove that this is not a clot? Well, I think we've proven through the UV that it is a clot because it lights up. When you hit it with UV, that's the iron saying, "Yeah, I'm here, and I didn't leave. Look at how tightly bound I am. Why am I not diffused? If I fell over and died," which is the way they paint it, walking along a river, just fell over and died, happened to fall in a river and got buried somehow. Your blood pools to the decumbent part of your body, closest to the ground. But we're finding clots throughout. So they drowned before they were put in place. And so another experiment that we're hoping to do is we're trying to find the finest grain iron filaments that we can, maybe 40 micron size we've found now, which might work on this picture. A grain would probably be maybe like that big. But what if we can magnetize those? What if we can magnetize this and put grains on it? Would they all orient north and south? That'd be a fun experiment, wouldn't it? So that's one we're working on. If you have suggestions, we're all ears. But we believe we found clots now. We believe we found how these organisms died. The next question is, when did they die? Right? Those are the two questions we're trying to answer, aren't we? How they died, when they died. Was it 6,000 years ago, 4,000 years ago, 10,000 years ago, a million years ago? That's the question, right, class? And the others, how did they die? Was it a meteor? Did they choke on ash? You know, were they smoking too many Luckies? Or was it a flood? Well, I think we show how they died by the clots. When you drown your blood clots. But how long ago? Well, I think the Permian helps us with this, and it's even older, according to them. We think it's all the same event. The flood was all one event. So this is a brand new paper that's in press. It says January 2023. We're obviously in February, but they run a little late. So this should be on the website. It's on our website. You can download it now. But it should be on Microscopy Today's website.